Okay, so we are starting our factoring sort of mini unit. We're just going to be doing this for about a week. Today is Friday. We have a quiz next Friday. So today, what we're looking at first is two of what I would probably call the easier types of factoring. And both of them are, well, one of them is very specific. The other is very general. So let me go ahead and focus and provide the visual that you need, and we'll jump into that. If you don't already have paper in front of you, you need that so that you can write down the examples we do. Your homework today is a Delta Math. Why are you not focusing? Very strange. I had to manually focus. Okay. Okay, so the first type we're doing, this is the one that I was saying is very general, is taking out a GCF. Now, one of the reasons I said it's very, or the main reason I said it's very general, is taking out a GCF is the very first thing you want to do anytime you're factoring anything. It doesn't matter whether it's a trinomial, a binomial, if it has 5 terms, anything. You always start by looking for common factors. And if there are common factors, you take out the biggest common factor. Okay, now taking out a GCF is the opposite, and you don't have to write this necessarily, of distributing. Okay, so for instance, if I had this, and I said, I'm going to multiply that, I would use the distributive property to multiply it. And I would say, okay, that's 8x plus 8 times 3. Taking out a GCF is going in the opposite direction. It's starting here and saying, what's my greatest common factor? And going there. So basically, your end product when you're taking out a GCF, so to speak, looks like you're about to distribute. It has a number out front. Now, you always want to start any kind of factoring by taking out any GCF. Sometimes, once you have taken out the GCF, what's left inside the parentheses can be factored further. And we will be doing some like that. Sometimes, that's all you can do. You know, you take out your GCF, there's nothing left to do. This can't be factored any further, so I would be done now. So sometimes the only factoring that can be done is just taking out a GCF, and that's it. That's still considered factoring. Like, I frequently have things like, you know, this will be on a quiz or something, and the student will say, well, that can't be factored. Well, if you took out the 8, you did factor it. It just can't be factored further. Okay? But taking out a factor is factoring. That's what factoring is. Factoring is just pulling it apart. Multiplication is putting your factors together into a product. Factoring is taking that product and pulling it apart into its factors. It's like the difference between doing 2 times 6 is 12 and 12 equals 2 times 6. Okay, that's all you're doing with factoring. So looking at taking out a GCF, a lot of times we tend to do it intuitively. Like for instance, let's say you have that. Okay, 14x minus 21. What we very often do is we say, what goes into, is there anything that goes into both of those terms? And just looking at it, most of us would probably see that what does? 7. So that's kind of an intuitive way to say, okay, yeah, 7 goes into both of those. So I'm going to take 7 out, and that leaves me with 2, and it leaves me with 3, and then I'm done. Notice that whatever's left behind when you factor always has the same structure as the original polynomial. In other words, my original polynomial had 2 terms and a minus. What's left inside here has 2 terms and a minus. Now, the minus can be different because you can factor out a negative. But generally, if we're factoring, well, sometimes we do. So you can change the sign. But if you're factoring something with 2 terms, you're going to have 2 terms inside of here after you factor. Okay, so keep that in mind. Now, sometimes people are like, okay, I'm just not seeing this. Okay, I think most of us tend to be fairly intuitive about simple GCF problems, but when they're more complicated, or if you think you're pretty intuitive about it, you're fine with just, looking at it and saying, what's the biggest common factor, but you keep getting one that's wrong, then instead go ahead and start trying to break it down. In other words, I'm going to break this down into all of its factors. 14 is 2 times 7, and both of those are prime numbers. So I'm going to say this is 2 times 7 times x minus 21 is 3 times 7, and both of those are prime factors. So that's what I get. In other words, these are what I would get if I broke this down like a factor tree, your prime factorization. Then what you can do is you can say, is there anything in both of them? Yes, that's what comes outside. And what's the beautiful thing here is not that part. The beautiful thing is when you do it this way, whatever hasn't been circled is what stays inside. That's whatever's left inside the parentheses. Okay, and sometimes that's what people have trouble with, is what should be inside the parentheses after you take something out. 2x minus 3. Like everything that's left is what goes inside. Okay, here's another example. And again, if you want to do this sort of intuitively, that is absolutely fine. If you look at it and say, what's my greatest common factor, or what goes into those two terms? Great. But don't forget to think not just of numbers. If you're going to ask yourself that question, what goes into both of these terms? Ask yourself, what's the biggest number that goes into both of these terms? But also, what's the biggest variable? Are there variables that go into both of these terms? And since this is m squared and this is m cubed, then m squared goes into both of those. Okay, so what number goes into 24 and 15? 3. So I'm going to take 3m squared out. And that leaves me with 8 minus 5m. And again, if I have any trouble seeing that, I can always, and I hope this is dark enough, let me see. I'm all out of felt tips. So it's like I want something in between this and in between and a marker and a regular pen. But that's my felt tip. So this is 24 is 4 times 6. And both of those can be broken down further. So I'm going to say that's 2 times 2 times 2 times 3. That's the prime factorization of 24. And this is 3 times 5 times m times m times m. And there's a minus between them. Okay, so the only number they have in common is the 3. Then they have an m in common. Then they have another m in common. M times m is m squared. So that's what made me decide to put 3m squared out front. Then what's left here is 2 times 2 times 2 is 8. There's a minus, and there's a 5m. So just using that method, this is really just sort of an algorithmic way to do it. In other words, if you're stuck on one, if one is a little bit more complicated, or for whatever reason, you're just not seeing it, you can always break it down like this. Break it down into its prime factorization and then circle the common factors. They go out front, and whatever's left stays inside the parentheses. Okay. I find that most people tend to not want to go to that extent, and I understand that. But most people tend to need to do it more often than they realize. Oh, let's do another one. Okay. So let's just go ahead and do it this way to begin with on this one. This is 2 times x times x times y. This is 2 times 2 times 2 times x times y times y. And there's a plus between there. So I know I'm going to have two terms with a plus between them and something out front. The something out front, 2x That's my common factor. 2xy is in both of them. And when I take out the 2xy, what's left here is an x plus 2 times 2 times y. That's 4y. So that's my answer. Let me write it a little darker. Okay, all the examples I've given you here were binomials, meaning they were two polynomials with two terms, 1, 2, 1, 2, 1, 2. Remember that in a polynomial, my terms are the things divided up, or excuse me, the things that are separated by pluses and minuses. Okay, but you don't just have to take out GCFs from binomials. You could take a GCF out of a polynomial of any number of terms. And sometimes, and this is just sort of random side example. Well, we can call it example 4. Why not? It is an example, and we are on 4. 10a squared plus 2a, no, excuse me, 20a minus 45. So we could take a GCF out of trinomials, and very often we have to. So no matter what it is we're looking at, you always want to first look for GCF. Okay, always look for GCF first when you're factoring. So what's the greatest thing that goes into all of those? 5. Okay, 5 goes into 10, 5 goes into 20, 5 goes into 45. So that leaves me with 2a squared plus 4a minus 9. Remember that whatever you get here, you can sort of check yourself by thinking of distribution. Like what would happen if I distributed this? This times this needs to equal that. This times this needs to equal that. And this times this needs to equal that. Okay, 5 times 2a squared is 10a squared. 5 times 4a is 20a. 5 times 9 is 45. And the signs need to make sense too. Very often at this point, what's inside the parentheses could still be factored. If it can be, you need to do that. Okay, this particular one can't, but sometimes, very often actually, they can be. So sometimes if it could be factored further, let's say, I don't want an example. Let's suppose that it could be. Then you would leave that 5 out front. The 5 would still be out front, but then you could factor it further into, you know, a plus 3 times a minus 6 or something like that. This one doesn't. This one is done here. But you can very often go on and factor what's inside the parentheses later, further, keep going. So once you take out a GCF, you always want to check to see if you're done or if what's inside the parentheses can be factored itself. You're done with whatever you took out front, but that's just staying there, holding on, waiting for you to finish the rest of the problem, and it will be out front in your answer. Okay, questions there? All right, I'm going to give you a few to try real quick. Just 4. Make sure I don't use any. Factor out a GCF. Now, a lot of times that you have to factor out a GCF, just for future reference, to keep it in mind, you're not told that you have to. You're just asked to factor. And you always, always, always check first for a GCF. All right, try those 4. let's go ahead and check these real quick. For the first one, this is what I get. For the second one, this is what I get. For the third one, this is what I get. That's a 3. And for the last one, that's what I got. Questions on any of those? Let me know if there's one you want me to just go through in more detail. I'm happy to do it. Yes, ma'am. 3, absolutely. That's probably my preferred one to go into more detail with. Seems to be begging for it, right? Okay, let's look at this. All right, we've got 6 is 3 times 2. Then we've got 3 A's and 2 B's. Minus 12 is 3 times 4, so 3 times 2 times 2. And we've got an A and then 5 B's. All right, so this common factor. I've got a 3, I got a 2. No other numbers in common. I have an A, no other A's, and I got 2 B's in both of them. So 3 times 2 is 6, and then I've got an A and then 2 B's. So that's how I know that's my greatest common factor. And then what's left inside, excuse me, A times A is A squared minus 2 times B times B times B, which is B cubed. Okay? Number 3 is the perfect example of the type of problem that I might be more likely to do this method on rather than just trying to look at it. Okay? Questions on any of them? Any other ones? Okay, the other method we're going to talk about today, which is a very, as opposed to how broad GCF is, meaning that you always should be paying attention to whether or not there's a GCF, this is much more a special case. And the special case is called the difference of 2 squares. Very often we just say the difference of squares. But I'll put the 2 in there for right now. Okay, which basically means something squared minus something squared. It means what it says. A difference means minus. Squares means things that are squared. Okay, so if you have something squared minus something squared, it always factors the same way. And we tend to write it out this way. We write it like A and B are my things that are squared. And that's always gonna factor as A minus B times A plus B, or A plus B times A minus B. It doesn't really matter where the plus goes. But you have the same thing, both places, and then there's a minus in one place and a plus in one place. Okay? The reason for this, let's just do one real quick in reverse order. The reason this works this way and the reason it's special is because if I multiply 2 binomials, which is what this is. Binomial is 2 terms, binomial 2 terms. If I multiply 2 binomials, most of the time I get a trinomial. I end up with 3 terms. Okay? But when I do it, and remember the way we usually do that, sometimes we call it distributive property. We do it in the order of distributive property. Sometimes we call it FOIL. But when we multiply 2 binomials, the first term is always going to be this times this. The last term is always going to be this times this. The middle term is always these guys multiplied plus these guys multiplied. And when those are the same with just opposite signs, I get 7x for one of them and negative 7x for the other one. And when I combine those like terms, basically they disappear. So that I'm not left with, usually I combine my 2 middle terms and I'm left with 3 terms overall. Here, I'm only left with 2 terms because the middle term disappeared completely. So that's the idea between or behind why all of this always factors the same way. Okay, is because if I have a binomial, only two terms, and they're both squared, that means that I basically multiplied two binomials that were the same except they had opposite signs, so the middle term canceled out. Okay, so for instance, if I have x squared minus 9, I want to make sure I use the examples I wanted to use. Okay, this is, and you don't have to rewrite it every time, but this is x squared minus 3 squared. So my a is x, my b is 3. And the way that factors is x times x in front, 3 times 3 in the back of each parentheses, and then one of them gets a plus and one of them gets a minus. Does not matter which is which. Okay, so let's say it's a squared minus 81. Okay, a squared minus 81. That's a difference. It has to be a minus to be able to do this. Has to be. Can't be a difference of two squares if it's not a difference, period. Okay, so this is a times a for the first term. And 81 is what times what? 9 times 9. And then plus and a minus. And anytime you doubt yourself with factoring or want to check yourself with factoring, remember you can check it by multiplying it back out. I could go ahead and do like FOIL here. And I would get a squared plus 9a minus 9a minus 81. So the plus 9a and the minus 9a would cancel out, or add to 0 is technically what we should say about that. You really need to be familiar enough with these that they sort of jump out at you. Okay, one clue to look for them is that you have two terms, because a difference of a difference of squares is always two terms. Something squared minus something squared. So that's a clue that you should be looking to see if maybe you have a difference of two squares. But what should you always look for before you look for anything else? I said it like 17 times about 10 minutes ago. A greatest common factor. Always look for a greatest common factor no matter what else you're going to do to factor. And this one has a greatest common factor. If you have two even numbers, you know you've got a greatest common factor of 2, if nothing else. So 2 comes out of both of those, which leaves me n squared minus 36. So here's a prime example of one that once I take out the GCF, what's left behind in parentheses still factors, because this is the difference of two squares. Okay, I've got two terms, and anytime I have a binomial, look and see if it's that, if it's the difference of two squares. It is. It's n squared minus 6 squared. So that's going to be n minus 6, n plus 6. It doesn't matter whether you put the minus or the plus first, either way. Another thing to be aware of is when you're asked to factor, there's an implied completely in there. Anytime you're asked to factor, the implication is we want to factor completely. Like you have factored when you take out the 2, but you're not done. There's more you can factor. So you always want to factor as much as you can. If there's more that can be factored, you should be doing that. Okay? Questions on that one? All right, let's try another one. Let's look at okay, it's two terms. So first thing I always look for is a GCF. I don't have a GCF. If I don't have a GCF, or if I've already taken care of the GCF, the next thing I always look for with two terms is whether I have two different perfect squares and there's a minus between. There's definitely a minus, so it is a difference. And this is something squared, and so is this. This is 3x squared. This is 3x times 3x. This is 5y squared, 5y times 5y. So my answer is going to be 3x plus 5y times 3x minus 5y. Questions on any of those? All right, 4 practice problems, just like last time. Make sure I don't give you a practice problem. We already did. That's an a squared. Sorry, it kind of got filled in. And that's an x. Okay, so factor those 4, please. And they are all differences of squares. So you're practicing the difference of 2 squares or factoring the difference of 2 squares. You guys ready to check these? You look ready. Okay, x plus 2, x minus 2. M minus 7, M plus 7. This one, a 5 comes out, and then we have a squared minus 16. So a plus 4, a minus 4. And this one would be x minus 2y, x plus 2y. Okay, notice that sometimes I started with plus, sometimes I started with minus. That is to underscore the fact that it does not matter. Either way is fine. Why is either way fine? Because multiplication is commutative. Okay, commutative property says you could do it in either order, and it means the same thing. 3 times 5 is the same as 5 times 3. Questions on any of those? Okay, so you have a Delta Math that practices exactly the types of factoring that we did today. You need to get that done sometime over the weekend. We're going to have an assignment every day for these because practice is necessary for factoring. There's 2 reasons to practice something, folks. There's one expression I heard that I love, and it was actually used in a musical context, was most people tend to try to practice until they can get it right. But you really need to practice until you can't get it wrong. Okay? One of the reasons we practice is to make sure we know what we're doing. The other one is to make sure we've done it enough times that it's almost like muscle memory, and we're not going to forget it if the test is 3 weeks from now. Okay? So keep that in mind when you're like, I don't need to do 5 of these problems, which I understand. Sometimes you don't. But sometimes doing 5 is what will help you remember how to do that type of problem 2 weeks from now or at the end of the exam when you're doing the final exam. So keep those thoughts in mind. And otherwise, have a great weekend. And I will see you on Monday. Again, virtual people, you can join us Monday. Otherwise, look for a posting of a recording of what we talk about in class, which will be factoring trinomials that have a leading coefficient of 1. That's what we're going to work on Monday. So have a great weekend.